Okay, so this is a brace frame, one level subframe method. The framing plans, this is the framing plans for a multi-story building, multi-story because it is more than one level, are shown in this figure. The main dimensions, structural features such as load, material and others are also set out as the given data. You need to analyze subframe 3AD level 1. So this is 3AD level 1. Okay, level 1. To determine shear forces and bending moments of corresponding beams and columns, use all three methods for analysis. So there are three methods. First is the one level subframe. Second is the 2.3 subframe. And the third method is 1.3 subframe. So the one level subframe method is quite complicated compared to the 2.3 subframe. The 2.3 subframe is the alternative method to one level subframe. Okay, so given the data here, the design life for this multi-story building is 50 years and constructed for permanent office building. The slab thickness is 150 millimeter. Column size is 300 to 400 millimeter. The QK given is 4 kilonewton per meter square. Finishes ceiling services, which is the GK, is equal to 0.75 kilonewton per meter square, and partition, which is the QK, because you can change the location of the partition, so it is QK, thus the value, and the value is 0.5 kilonewton per meter square. Okay, so the beam grid line 1 to 12. So grid line 1 to 12. So grid, this is 1 to 12. This is the grid line 1, 2, 3, 4 until 12. So all beam here, the size for this beam is 250 times 600. Okay, BH. Okay, and meanwhile for the beam in grid line ABCD, this is grid line A, B, C and D. The dimension for this beam is 250, 50 and 500 millimeter height. Okay, width, height. Okay, so this is the proposed size for beam in grid 1 to 12 and beam grade A to D. Okay, so meanwhile for this information later used in umbrace example. Okay, umbrace frame. Okay, so you need to analyze, you need to determine the shear forces and the bending moments here for the subframe 3AB. So this is the subframe. So this subframe have three span. Okay, three span. So this is the span. Okay, from this either this view or this view lah kita pandangkan. So kita akan nampak ni. So you need to design level 1. Level 1. Okay. So if you look here, okay, if you look to this plan view ni kan. So this beam is connected with the slab 2-3 and 3-4. So this slab. Okay. So even though for frame analysis, the 2D view only have beam and column, please take note that beam here receive load from slab. Okay, load on slab will be transferred to the beam, depends on the one way or two way. Okay, determination. Okay, boleh ya. Okay, and the length, the length for this span, okay, is 6 meter. Okay, this one 6 meter, 6 meter, 6 meter. So all span is equal. Okay, 6 meter, and the height for the column, this column height is 4 meter, and after level 1, each column having height of 3.5 meter. Okay, tinggi ni 3.5, 3.5, 3.5, and the bottom level is 4 meter. And next, calculate. The first one is to calculate the action on slab. Okay, this is action on slab. Okay, listed here is the specification as given in the question. So this is the finished ceiling, density of concrete. We know that the value is 25 kilonewton per cubic meter, and imposed loads given 4 kilonewton per meter square, and this is partition, and given the dimension for slab, beam and column. Okay, so first you need to distribute slab loading to beam. This slab, okay, loading acting on this slab is distributed to this beam 3D. First you need to check the long span to the shorter span, either it is less or more than 2. So for slab 2, 3, so this is slab 2, 3, 2, 3, A, B. So this is A, B, C, and D, 4, 3, 2. Okay, 4, 3, 2, this slab, and also A, B, C, D. Okay, A, B, C, D. Okay, slab 2, 3, 2, 3, A, B. A, B here is slab number 1. Okay, so slab 3, 4, A, B, slab number 2. Okay, so here is slab number 3. So saya labelkan senang lah macam ni 4, 5, and 6. So this is 1, 2, 3, until 6. Okay, so the first slab here, it is Lx Ly divided by Lx equal to 1.5, which is less than 2. So the next one is the second slab is 6 divided by 5. The third slab is Ly divided by Lx, and continue until slab number 6, which is 6 divided by 5. So all slab is less than 2, thus all slab is the two-way slab. Okay, two-way slab, you can refer to British Standard 8110 using table 3.15 to determine the shear. Okay, the shear is in kilonewton, so we distribute the loading to this beam using table 3.15, and the formula for the shear loading, okay, shear at x-axis is beta Vx multiplied with this is the design load, okay, design load multiplied with the Lx, okay, the shortened length. Okay, so meanwhile for here, for the in the y direction, okay, for the y direction, beta Vy and Lx. Okay, so if you look here, so this is slab number 1. Slab number 1 is here is the long edge, shorter edge, short edge. So one short edge discontinuous. So one short edge discontinuous is case number 2. Okay, this is discontinuous. Okay, this slab and this slab is similar. Okay, short length, short edge, short edge. Okay, so this one and this one is similar, thus the value here should be same. Okay, and here is the 5 and 6. Okay, similar with slab 1 and 5. Slab number 2 also is case number 2, where the one short edge is continuous. So case number 2. Okay, and we go look at slab 3 and slab 4. Okay, slab 3 and slab 4 is in the middle. Okay, so here is slab 3 and slab number 4. Okay, so it is continuous with other slab, thus all 4 edges continuous. 4 edge continuous is case number 1. Okay, so this is case number 1. Okay, case number 1. And then we determine all this number. Okay, this beta. Okay, beta Vx and also beta Vy. Okay, so this is the shorter length. So this is in X. And here is in Y. Okay, in Y. So in X here, for the X here is 1.5. 1.5 here. So one short edge, 1.5 here. And case number 2. And the value is 0.47. So here is 0.47. This value is similar with this value. Okay, because the case is same. Okay, so 0.47, 0.47. Okay, for the continuous edge. This is continuous edge. Okay, so meanwhile for this slab, number 2 and number 6 is similar. Okay, so for this one, 6 divided by 5 is equal to 1.2. 1.2, thus the value is equal to 0.42. Okay, so this is 1.2, case number 2. So the value is 0.42. So this is 0.42, 0.42. Meanwhile, for the middle span here, okay, surrounded with the slab at all edges. Okay, all edge. Okay, so this is slab number 3. Slab number 3, so here is X. Okay, and here is Y. Okay, so X here, continuous here. So here is continuous edge, 1.5, so equal to 0.45. And the beta Vy is 0.33, but however we are in the X direction here. So thus we select 0.45. So 0.45. Okay, so and this value is equal. Okay, so here 0.5, 0.45, 0.45. Okay, and meanwhile for here is 1.2. Okay, 1.2 here. Okay, so 1.2, the value for beta Vx is 0.39. Okay, 0.39 kat sini. Okay, we have determined all the value for the beta Vx. Okay, next is calculate action on beam. So first you need to calculate the slab. Okay, because the process of flow of the loading is from slab to beam. So you need to calculate or determine slab load first. So this is slab. Okay, then later baru you check for the beam. Okay, so this is slab. So for example, let's say this is the slab here, and under the slab here is the T-beam. T-beam kat sini kan. So this is thickness for slab. Thickness for slab is 150, and the beam here, the size here is 250. And the total height for the beam is 600, sorry, 600. Okay, so 600. Okay, so this is the beam, and this is slab. Okay, slab. So load from slab is transferred to this beam. Okay, either in two-way or one-way direction. So in this case, in this example, it is two-way. Okay, slab. So the slab self weight is equal to the thickness slab thickness 150 multiplied with the concrete density, we get 2.75. Finishes ceiling and other dead load, okay, on the slab given is 0.75. Thus total GK for the slab is 4.5. Okay, slab. Okay, meanwhile for the imposed load given in the questions 4 plus the partition 0.5 and total QK acting on slab is 4.5. Okay, total QK and this is total GK. So all loading, okay, transfer to this beam here. Okay, so this beam will receive GK and QK from side A and also side B. The same value GK and QK, the difference is at the beta Vx. Okay, beta Vx. Okay, alright, so this is the loading. Okay, the GK and also QK, unit in kilonewton per meter square. And then next is determine loading on beam. Okay, loading acting on beam. Okay, loading acting on beam. Okay. So first is the span number 1. Span AB. Okay, this is AB. This is span number 1. Span number 1, load transfer from slab. Okay, load transfer for slab. So divided into 2 parts here. So this is the GK and also here is the QK. Okay, so first you need to determine the total GK. So permanent load from slab and also permanent load from slab 1 and slab 2. Why there are 2 slabs? Because if you look here, so this is span AB. Span AB receive load from this 0.47 and 0.42. Slab number 1 and slab number 2. So this is slab number 1. Slab number 1 is beta Vx multiplied with the GK, and the GK here the value is 4.5 multiplied with the Lx. Okay, and the second slab is, this is the second slab, 0.42 multiplied with the GK, okay, multiplied with the Lx for slab number 2. The beam self-weight here is 0.45 multiplied with 0.25 multiplied with the density for concrete. So this is the size for the beam. So the self-weight of the beam, beam self-weight is, the size is 600 minus thickness, slab thickness. Okay, I multiply with 250. So this is 4.5 multiplied with 0.25. Okay, and finally we got the total GK. Total GK acting on slab. First slab is equal to 20.72. So next is the variable load from slab, the QK. The QK is beta Vx. Beta Vx multiplied with QK. So here is the QK. And value for QK is 4.5 multiplied with Lx. Okay, so this is from the second floor. Okay, multiply with the 0.42, 4.5 and 5 Lx. And finally we get QK for slab number 1. QK here is equal to 17.91. And we multiply with the partial safety factor, which is 1.35 plus 1.5 for the maximum load and 1.35 GK for the minimum load. So this is maximum load, this is minimum load, and this is the value. So next is the span BC. So span BC, first is a transfer loading from slab GK to beam. Okay, so here is the process. Okay, beta multiply with the N multiply with the LX. Okay, and here is the GK. Okay, GK. This is slab number 4. Okay, and the beam self weight. And finally, we got GK is equal to 19.69. Okay, please don't round it. Okay, jangan round it up, jangan ya. Okay, so 19.69. Okay, next. For span 2, the QK, this is slab number 3 and slab number 4. Okay, and the characteristic load for the QK slab number 2, beam number 2 is equal to 16.88. And finally, we calculate the maximum load and also minimum load. Substitute this value and this value into this equation. Okay, next is span number 3. Span number 3, okay. So this is the GK. Okay, GK is the total of loading from slab and the beam. Okay, so this is slab number 5 and here is slab number 6. Okay, so beta multiply with GK multiply with LX. And finally, we get the total GK for span number 3 is 20.72. So next is the total QK from span to beam is, this is slab number 5 and here is slab number 6. Okay, so beta Vx multiply with the, here is the QK multiply with LX. Okay, and same calculation for the slab number 6. Okay, and finally we got total QK is equal to 17.91, and substitute these two value into this equation, and we get the maximum load is 54 and the minimum load is 27. And to make it easier to proceed with the next analysis, okay, you copy this one, okay. Next, copy this value and also this value and summarize it as shown here. So this is the summarize. Okay, the final output from this analysis. So for W1, so this is W1, W2 for span number 2, and this is span number 3. So for each span, given here the minimum and also maximum, maximum, okay, according to the span. So the beam size here is 250 plus to 600 millimeter BH. Okay, and column size is 200, 400. So this is important for you to calculate the moment of inertia. So moment of inertia is later will be used in the stiffness determination. Okay. Okay, next is to determine the moment of inertia. Okay, before I proceed with this one, you in this frame analysis, you will use moment distribution method. Okay, so under this moment distribution method, you need to know K value. Okay, kemudian next is the distribution factor and also the fixed end moment. So this is important value, and to get the K, you need to know the moment of inertia, and when moment of inertia for each span is divided by L, so this is stiffness. Okay, stiffness equation. K is stiffness, and F is the distribution factor. Distribution factor is the stiffness divided by total stiffness, and this is FEM based on the loading, based on the loading type lah, point load ke UDL dan sebagainya, or combination of point load and UDL, for example. So first we proceed with this one, moment of inertia. Moment of inertia for beam and column, because we only have one size for beam and one size for column. Okay, thus calculate only once. Okay, so for beam, the moment of inertia for beam is B multiplied with the 6 power of 3 divided by 12. So everyone know that the equation for the moment of inertia for the square shape cross section is BH power of 3 divided by 12. So this is column. Okay, column, and result for the moment of inertia as given, as shown here. And next is the stiffness. Stiffness is K equal to I divided by L. Okay, divided by L. So this is the span, continuous span. So, and each of this span is equal to, the length is 6. Okay, the length is 6. Okay, and also the span at every joint have column. Okay, so this is column. Okay, fix here. So this is upper column, and here is the beam, and here is the lower column. Okay, lower column. Yeah, so the symbol is, here is KAB, because here is joint A, joint B, joint C, and joint D. AB, so stiffness AB, stiffness BA, BC, stiffness BC, stiffness C to B. Okay, then stiffness CD, C to D, and stiffness D to C. Meanwhile, for the upper column here, we have K, CU for the upper, U stands for upper, and KCL. Okay, L is the lower. Okay, depends lah, kalau lepas ni you nak buat, this is the top, KCT. Okay, this is the upper, this is the bottom, KCB. Okay, it just the labeling. Okay, but for the K, you cannot change. K is the level, is is for the stiffness. Okay, so the KCU is I divided by L. So I divided by L, K. So KCU is the upper, so the column moment of inertia is 1.6. Okay, 1.6 divided by L. L is equal, here is equal to 3.5. Okay. Okay, so this is the upper. Column. So the size for the upper column is from here to here. Okay, each column has the length for each column is 3.5 meter. Okay, 3.5, and the bottom column here, this lower column is 4 meter. Okay, so divided by 3.5. Okay, 3,500. So we get 4.6. Okay, meanwhile for KCL, I divided by L, so 4, and KAB equal to KBA. Okay, we get 7.5. So because the length is same and the size also same, thus all span here, all three span have a similar stiffness. Okay, so which is 7.5. Okay, so next you need to calculate the distribution factor. Distribution factor, for example, joint A. Joint A. So this is joint A. Okay, joint A here, if I take keluarkan sini, so this is joint A. A. Okay. So K here is 4.6. Okay. And meanwhile for the lower K here, for the column, lower column is the 4. Okay, 4. And KAB here is 7.5. Okay, so to determine the FAB, okay, distribution factor, FAB here, for beam FAB. Okay, so here is the FCU, and meanwhile here is FCL. So first determine the FAB. So FAB, the distribution factor F is equal to FAB divided by total distribution factor at joint A. Okay, so FAB plus FCU plus FCL. F 7.5 plus 4 plus 4.6. Okay, so equal to 7.5 divided by 7.5 plus 4.6 plus 4, and this distribution factor for FAB is equal to 0.47. Okay, so same goes with the B here. So saya tunjuk lagi satu contoh ya. Okay, let's try B. Okay, B. So here is joint B. B here, and this is fixed. Okay, so B here is, let's say you want to determine KBC, want to determine FBC, sorry, FBC. Okay, FBC, so here is FBC. Okay, here is FBA. Okay, here is FCU, and down here is, below here is FCL. Okay, FCL. So FCU here is equal to KCU 4.6. Tak apalah, nanti kita tengok lah. Okay, let's say you want to determine the distribution factor for FBC. Or for FBC is equal to KBC divided by 1, 2, 3, 4. Okay, KBC plus KCL plus KBA plus KCU. Okay, so KBC is 7.5. Okay, 7.5 KBC, KBA. So divided by 7.5 multiply with 2 plus KCU, KCL. Okay, 4.6 plus 4.0, and finally we get FBC here is equal to 0.32. Okay, so later you can check for each distribution factor. Okay, boleh ya? I show to you two example only. Okay, for at B and also A and also B. Okay, we have determined the distribution factor. Next, we proceed with the case 1, case 2, case 3 for the to determine the shear and also moment. Okay, so if you still remember class on Sunday, okay, so I mentioned to you, I told you that there are 4 cases of the load arrangement. The first one is maximum, minimum. Next is the minimum, maximum. Next is the maximum. The third case is maximum. Second span is minimum, and the third span is maximum. Okay. And the fourth case is minimum, maximum, minimum. Okay, so this maximum and minimum, so the first case is maximum, minimum, maximum. Maximum, minimum, maximum. And this value, maximum, minimum, maximum, for each span, okay, has been calculated here. Okay, so you have summarized the output. Okay, in this, kita panggil apa ya, table lah. Okay, So here is the maximum and minimum for span number 1, okay, 2 and 3. Okay, first look at case number 1. So case number 1 is the load arrangement is maximum, minimum. So why need at least 4 load arrangement? So this is because we want to determine the optimum, okay, shear and also moment at column. Okay, boleh ya, and also beam lah. Okay, so maximum. So this is maximum, minimum. So this is span number 1. Span number 1, the maximum value for span number 1 and span number 2 is, okay, span number 1 here, span number 1, W1 here, so W1 is 54.8, and W2 here, the maximum is 51.9, and span number 3, the minimum is 28. Okay, so this is all the maximum and minimum value. So the lower column height is 4 and the top column height is 3.5, and each beam has 6 meter span. Okay, so you need to, next is to calculate, to determine the fixed and moment for each span, because you want to proceed with the moment distribution method, thus you need to determine FEM, fixed and moment. Okay, for this first one, this is the span number 1. Okay, span number 1. Okay, so both end is fixed. That is why we call fixed end. Fixed end, both is end, moment. Okay, so loading here is go downward. Okay, go downward 54.8. When this load go downward, so we assume that the moment should be this way. Okay, okay, sebab yang ini kan ke bawah, so dia kena nak seimbangkan. Okay, alright. Okay, and this is MAB because here is joint A and joint B, and here is moment at BA. So this is how we draw the fixed end moment for span number 1. Okay, so next is span number 2. Okay, span number 2. This is span number 2, fixed end moment. Span number 3, fixed end moment. Okay, loading here is 51.9. And loading here is okay, 28. Either you draw it like this, the UDL, or you draw it like this. Okay, both can. Okay, and the length here is 6, and also 6. Okay, fixed end moment. Okay, and here is B, C, C, D, and the direction for the moment is this way. So here is M, B, C, B to C. Here is M, C, B, C to B. And the third span is M, C, D. And here is M, D, C. Okay, let's go back to the first span. So the first span is MAB. So formula for the UDL, for UDL is WL power of 2 divided by 12. UDL. If there is combination of the point load, let's say here is point load here, so plus PA power of 2 B, okay, di plus lah L berapa bawah saya lupa. Okay, so this one, okay, this is MAB is equal to MBA. MBA, the value should be same because the loading, it comes from the same loading. Okay, so 54.8, but the difference is the direction of the moment. So if you look here, this is counterclockwise. So counterclockwise, thus this is negative. Okay, this is clockwise, positive. And we got the fixed end moment for here is 54.8 negative. This is positive. Okay, same goes to the second and third span. Okay, third span, this is counterclockwise negative. Here is clockwise positive. Okay, next we proceed with the moment distribution method. Okay, moment distribution method. Okay, look at this carefully. Okay, sebenarnya saya dah sediakan ini, tapi dia tak complete kat sini tak complete. Okay, tak apa, saya fokus pada ini sahaja. Okay, so here, so this is join A, join B, C and D. Okay, join A, B, C and D. A, B, C and D. Okay, so this is join at N, A and D. Okay, so dia tak ada lagi satu kat sini lah. Okay, so this for the N join. Okay, N join which is A and D. So this is column. This is represent column. So this is the boundary. Okay, boundary. Okay. This is bottom column. Lower column. And here is top column. Okay, 1. This is top column, bottom column. Okay, so this is the boundary. Okay, top column, bottom, lower column, upper column. Okay, and then here is the beam. This one represent beam. This column represent beam. Okay, so here is beam AB, here is beam BC. Okay, BA. Okay, so this one is represent AB, BA, BC, CB, CD, and also DC. So this is how to read this arrangement. Okay, so please imagine that all value inside here is empty. Okay, there is no value here. So the first step is to insert the distribution factor, and this is the distribution factor. So look one by one. So this is join A. Join A. So this is beam, upper column, lower column. Okay, so beam here is 0.47, right here 0.47. So this beam AB, distribution factor. So this is the distribution factor. FCU is the distribution factor for upper column. Okay, mana dia? So this is distribution factor for the upper column, which is 0.28. Okay, 0.28, and lower column is 0.25. Here the lower column is 0.25. This is the upper column, 0.28. And then you continue with join B, C and D. Okay, so for the B, join B, there are 4 sides. So this is for the beam. Okay, FBC, here is FBA, here is the FCU, and here is FCL. Okay, so this is joint B, FBA, FBC, FCU, and FCL, and this is the value. Okay, done for the distribution factor. So next is the fixed end moment. So we get here the fixed end moment. Fixed end moment for MAB, MBC, MCD. So MAB, is 164.5. Okay, 164.5, this is AB, moment at AB, so this is moment. So we write moment at this row, all the FEM. Okay, so here's the MAB. FEM at AB is equal to negative. Please do not ignore negative sign. Okay, so here is negative. MAB, moment at AB, okay, is negative. Moment B to A is positive. Okay, 164.5. Okay, so this is the column row, the column for the column. Okay, so leave this one empty and proceed with this BC. So moment at BC is 155.7. Okay, so this is BC. Please take note the negative sign here, 155.7, and MCB is positive. Okay, so thus here is negative 155.7, here is positive, and this is the same definition lah, similar lah. Okay, so at point C here, MCD here, and MDD. Okay, okay, all value for the K here, the stiffness here, distribution factor is added. Okay, has been added here, and here is the FEM. Okay, so done, and we proceed with the process moment distribution method. Okay, first please take note there, please look it clearly. So this is 164.5. Okay, 164.5. So this is joint A. Okay, joint A. And moment is negative. So negative is this way, counterclockwise. Okay, 164.5. Okay, 164.5. So we need some value to make sure that this joint is in equilibrium condition, which is equal to 0. Okay, dengar ya. So this is negative. Saya letak negative. So 164.5. Okay, to make sure that this joint is in equilibrium condition, we need another 164.5. Okay, we need another 164.5 in positive. So negative plus positive, same value, is equal to 0. So we need additional 164.5 on at joint A. Okay, at joint A. Okay, 164.5. This 164.5 we distribute equally based on the distribution factor. Okay, we distribute based on this distribution factor to the beam, to the lower column, and also to the top column. Okay, so this is top column, this is lower column. Okay, column. Okay, this is beam. Okay, boleh ya. So ini ini kita punya reference. Okay, 164.5, 164.5. Okay, multiply with 0.47 and we get 76.8. Okay, so here is 164.5 multiply with 0.47. Okay, so we get 76.8. Next is 164.5 multiply with 0.25, and we get 40.9. Okay, so next 164.5 multiply with 0.28. Okay, we distribute this value about 46.80 to upper column. Okay, faham ya? So to check either the calculation is correct or no, so you this value, and this value, and also this value, total it all must equal to 0. Okay, if 0.005 is okay, 0.001 is okay. Kalau 0.1 you kena lihat balik. Okay, boleh ya? However, for this example, there are some you need to correct the value inside here. Okay, value inside here. It should equal to 0. Yeah, this I have calculated it yesterday. This one 76.8 should be, the value is 7732. Here is 41.125. Here is 46.06. When we total this one equal to 0. Okay, boleh ya? So equal to 0. So same goes here. Okay, same goes here. So for at point B here, so this is the reference for distribution. That is what we call distribution. We distribute the additional moment to column and beam based on this factor. Okay, based on this factor. Okay, all this factor at joint B. Okay, so this is what we call it, the fixed end moment. Okay, so this is joint B. Okay, joint B here. This is B. Okay, and moment here, here is positive. Positive is clockwise. Clockwise 16, clockwise betul lah sini kan? 164.5. And for BC, here is BC, here is BA, here is BA, here is BC. So B to C here is 155 counterclockwise. So here is counterclockwise. Negative 155.7. Okay, it's okay for you not to write the negative here because the sign arrow here show the counterclockwise, which means negative sign. Okay, counterclockwise. So between this one, 164.5 minus 155.7, and the value is equal to 8.8. Okay, 8.8 meaning this is the large value. It will rotate. Okay, joint A tends to rotate counterclockwise. Okay, because it has additional 8.8. Okay, to make sure this joint B in equilibrium condition, which is 0, no rotation, so we need additional 8.8, and this 8.8 should be comes from the negative sign, so we need another negative 8.8. Okay, 8.8. Betul kan? Saya buat simbol macam ni. Okay, 8.8. So 8.8 will be distributed to BC, to BA, to lower column, to the upper column according to the distribution factor. Okay, so we need another 8.8 in negative sign. So 8.8 multiplied with 0.32 is equal to negative 2.8. Done? Okay, 8.8 multiplied with the 0.32. Okay, so it equal to negative 2.8. Done? 8.8 multiplied with 0.19, so it equal to negative 1.72. Done? Okay, 8.8 negative multiplied with the 0.17 is equal to negative 1.5. Okay, 1.5. So we have distribute 8.8 to BC, BA, upper column and lower column. So to check either the calculation is correct or no, so this value, all this moment, so this is moment, okay, this is moment, plus this moment, okay, because this is stage 1, okay, must equal to 0. If equal to 0, then this is correct. Boleh ya? So C is similar and also this is the similar process. Okay, next we bring forward. Okay, bring to the left. Okay, then we get this one. So you draw this line. Okay, so this is the line. Okay, because this is one set, this is one set. Okay, next 2.8, move to the left, 76.2, carry forward to the right, divided by 2. 2.8 divided by 2 equal to 1.4. Please do not left behind this negative sign. And 76.8 is equal to 38.4. Okay, so nothing to transfer from here, so here is 0. Okay, same goes here, so divided by 2. Okay, divided by 2. And the process is repeating. Repeat process. Okay, so let's say here is 1.4 negative. It is the repeating process. This is 1.4 at joint A here. And negative, so it is counterclockwise 1.4 negative. So we need additional positive 1.4 to ensure equilibrium condition at joint A. So thus there is no rotation at joint A. Okay, so 1.4 positive will be distributed to AB, lower column and upper column based on the distribution factor given here. So 1.4 positive, 1.4 multiplied with 0.47 is equal to 0.7. Okay, 1.4 multiplied with 0.25 is equal to 0.4. 1.4 multiplied with 0.28 is equal to 0.4. And this value plus this value plus this value should equal to 0. Okay, clear? Yeah? So same process goes to this joint B, joint C and joint D. And next is to determine the shear. So this is the moment. Okay, sebelum proceed and finally when the distribution near to 0 lah, near to 0, so near to 0. Okay, distribution near to this still can be distributed. Okay, so and finally this is the moment, the total moment for each joint. Okay, so this is total moment. This is moment at lower, this is moment at the lower column, this is moment at the beam. Okay, for the CD and DC. Okay, boleh ya. So next is to determine the shear. Moment distribution done. Okay, so kita check for the shear. So this is the shear force. This is repeating ya. Sorry, saya tak tunjuk yang ini. So the shear force, this is the first span, second span and the third span. So the first one, the first span here using the moment. This is VAB. Here is VBA. Okay, saya tunjuk satu saja. So moment here is 91.1. Okay, VAB. VAB, this is AB, 91.1. Negative. Negative is important because when you know that is negative, thus the arrow is in this direction. Okay, and the VB here, VBA here, VA here is 191.3. VBA. So this is BA. BA here, moment is 191.3. Okay, so moment here is 191.3 and applied loading acting on the beam is 54.8. Okay, so because the first span is the maximum loading, okay, and the span is 6. Okay, so take moment at B. When we take moment at B, all loading move to bring to joint B, so equal to 0. Okay, so this is the same process on how to determine support reaction at at B and also A here. Okay, so saya rasa saya tak payah tunjuk lah. Okay, so tunjuk sikit lah. So this is negative, negative 91.1 plus 191.3. Okay, so done. So we have here 54. 54 move here is counterclockwise. So counterclockwise minus 54.8. So the length for the loading is 6. Okay, so to move to the, because moment is force multiplied with direction. Okay, length. Okay, and this one is 6 divided by 2. Okay, so equal to, oh sorry, lagi satu VAB So plus, this is positive. Okay, 6 VAB equal to 0. And finally, we got VAB. Okay, equal to 147.8. And next, you calculate VBA. So that is why it is important to know how to calculate the support reaction. It is very important. Okay, boleh ya. So this is at span A, span number 1, and this is span number 2, this is span number 3. Okay, boleh ya. So this is span number 3. So you read lah dia punya moment. So this moment is taken from this moment distribution method. And finally, this is the bending moment diagram and also shear force diagram. Shear force diagram sepatutnya ada 3 lah. Sorry, itu bukan, itu dekat last kali. Okay, so this is for the case number 1. So this is the final result for the case number 1. And then you proceed with the case number 2. The case number 2 is minimum, maximum, maximum. So the process is similar with the case number 1. Sama sahaja. First, you need to determine the fixed end moment. And then from the fixed end moment, using the same value for the distribution factor, okay, you analyze the frame using moment distribution method. And finally, this is the shear force and bending moment diagram. Case number 3 is maximum, minimum, maximum. Okay, maximum, minimum, maximum. Again, you need to calculate the fixed end moment for this combination case kan. Okay, then using the same distribution factor. Okay, so analyze this subframe. Okay, using the moment distribution factor, and you get this is the shear force diagram and bending moment diagram. So the same procedure to the case number 4, minimum, maximum, minimum. And finally, this is the final result. This is all combination from 4 cases. Okay, sepatutnya ada 4 lah, kat sini ada 4 ya. Ada 4 line, di sini ada 4 line, ada 4 line. Okay, boleh ya, so ada 4 line kat sini. Okay, so this is example 2.1 for the brace column, for the brace frame using one level subframe method. Thank you.